Welcome to online precalculus. Okay, we're going to start today with section P.1 Algebraic expressions, mathematical models, and real numbers. Okay, so we have a lot of different objectives that we're going to cover in this section. It's going to be a little bit longer. So first we're going to evaluate algebraic expressions, then we'll use mathematical models, then find the intersection of two sets, the union of two sets, and talk about set notation a little bit. Recognize then the subsets of all the real numbers. Then we'll go on to inequality symbols, absolute value, evaluating and use it to find distance, the properties of real numbers, and finally simplifying algebraic expressions. Okay? So first, what's an algebraic expression? Algebra, right? We basically replace numbers with letters like x and y to represent different numbers. If a letter is used to represent various numbers, we call it a variable, right? Because it's something that can change. We can put anything in there that we want. So the example here from the text is, imagine that you're basking in the sun on the beach. We can let X represent the number of minutes that you can stay in the sun without burning with no sunscreen. With number 6 sunscreen, exposure time without burning is 6 times as long, or 6 times X. Now, when we write stuff in this class, we're going to tend to not write the multiplication sign and pretty much write it as 6x. Okay, when we write it next to it, it implies multiplication. All right, so notice that 6x combines the number 6 and a variable x using the operation of multiplication. Combination of variables, numbers, and the operations of addition, subtraction, multiplication, division, powers, and roots is called an algebraic expression. These are all examples, all of them, they're all examples of algebraic expressions. Oops. Okay. So many different algebraic expressions involve exponents. For example, we have this expression 4x squared plus 341x plus 3194, which approximate, and we're going to use this later, this approximates the average cost of tuition and fees at public U.S. colleges for the school year ending X years after 2000, right? So if you're in 2005, you would plug in 5, right? 5 years after 2000. The expression x squared means x times x to the second power, x squared. That's the way we're going to pretty much say it all throughout this course. And the exponent 2 indicates that the base x appears as a factor 2 times. Okay, so exponential notation, no matter what my power is, you should recognize it, you should know how to use it, should be fairly familiar by now. Okay, we start with the base, that's the number down there, and the exponent or power is going to be smaller. We call that a superscript. We're going to write it in smaller notation, and it just means that you multiply b that many times. So b to the n is the nth power of b, and the nth power of b is defined as the product of n factors of b. The expression b to the nth power is called an exponential expression, right? Any expression that has an exponent is an exponential expression. And anything to the first power, the exponent just goes away. Okay, so those should all be fairly familiar, okay? And let's get in now to evaluating algebraic expressions. Okay, and this means to find the value of an expression for a given value of the variable. Okay, when we evaluate algebraic expressions, we're going to have to use order of operations. Okay, and the way we do it is, in case you forget, right, we have our little acronym that can help us, PEMDAS, parentheses, exponents, multiplication, division, addition, and subtraction. Now realize that for multiplication and division, multiplication is not more important than division, right? We always do parentheses first, innermost parentheses, and work outwards. If it involves a fraction, right, the numerator and denominator as if they were each enclosed in parentheses, that's something like 3 plus 4 over 2. Really, what we're saying is do the 3 plus 4 first, right? So if two things are over a fraction bar, that means that they are actually enclosed in parentheses, even if you don't see them. Then we're going to do exponents. Then we're going to do multiplication and division as they occur from left to right, and the same thing with addition and subtraction. So let's do some problems. Our first example is to evaluate an algebraic expression. So I know what x is equal to, right? All I have to do now is plug it in. So we have 7 plus 5 times, well, x is 6, minus 4 to the third power. Now I just have to be sure to do the order of operations correctly. Parentheses first, and then exponents don't multiply the 5 and the 2, right? Exponents comes first, so that's 7 plus 5, 2 to the third is 2 times 2 times 2, which is 8. So that's 7 plus 40. And so we have simplified, or we've evaluated this algebraic expression, and we now have that it is equal to 47. Okay? Let's do one more. We usually have a example and a second checkpoint problem. All right, so same idea. So 8 plus 6 times 13 minus 3 squared. So we have 8, 13 minus 3 is 10. So that's 100. And we have multiplication 600, so we have 608. That's my expression. Okay. Next, formulas and mathematical models. So an equation is formed when an equal sign is placed between two algebraic expressions, right? This is an expression, right? There is no equal sign, but as soon as you put something over here on the right-hand side that this expression is equal, or this thing is that expression is equal to something, it becomes an equation. One aim of algebra is to provide compact symbolic descriptions of the world. And these descriptions can involve the use of formulas. And a formula is just an equation that uses two variables to represent a relationship between two or more quantities. So if you look at these two people, right, there's just two formulas representing the heart rate of the type of exercise they're doing. So with the person who's not really working out, just pretending, you can see that the formula of their heart rate is 1/5 times 220 minus A. Difference between 220 minus your age. And even if this person is the guy doing push-ups, even if he is the same age, you can see that his heart rate is going to be much higher. This is multiplying by 1/5, right? Dividing by 5. This is multiplying by 9/10. So when you multiply by a larger fraction, it makes the number bigger. So the process of finding formulas to describe real-world phenomenon is called mathematical modeling, right? You might not have ever used these two formulas for heart rate before, but if it works to model the situation, if it works to give you an accurate representation of what's going on, it would be called a mathematical model. Okay? So let's look at a mathematical model. So we have the cost of attending a public college. So the bar graph down here shows the average cost of tuition and fees for a public four-year colleges adjusted for inflation. The formula is the one we talked about at the beginning, 4x squared plus 341x plus 3194. Okay. The graph gives us the actual data, right? The formula is a model. The graph is the actual data. Okay. So use the formula to find the average cost and tuition of fees for 2010. Okay, so the formula was that tuition is equal to 4x squared plus 341x plus 3194. Okay, so if I want to know what the tuition was in 2010, all I would have to do is plug in 10. So that's 4 times 10 squared plus 341 times 10 plus 3194. Exponents first, so that would be 4 times 100. We can just multiply these two together, 3410. and 3194. That turns into 400 after I multiply. And when I add all of these numbers together, I get $7,004. Okay, so that's what my formula says, that I have, that is going to cost me $7,004. But let's look at the data, and I see that in 2010, it actually costs $7,020. So by how much does the formula underestimate or overestimate? Well, the formula said I was going to pay less, so it underestimates by $16 because I thought it was going to, the formula said it was going to do 7,004, but the actual data says it's going to cost 7,020, 7,004. Okay. Same formula again. If I wanted to find 2015, right, all we would do is plug in a 15. 341 times 15. And now, okay, we'll just do this real quick. 15 squared, my trusty calculator. Gives me the tuition here is 9209. Unfortunately, there's no way to check the graph because it doesn't go that far. Okay, does my answer make sense? That tuition is growing? Yeah, and in fact, I should realize that since this is a positive leading coefficient and x squared means a parabola, means that this graph kind of is always going to be increasing as we go to the right, which unfortunately makes sense for the way colleges charge. It's always going to get more expensive, never really going to get cheaper. Okay. Sometimes a mathematical model gives an estimate that is not good, that's not a good approximation, or is extended to include values of the variable that do not make sense. In this case, we say that we have model breakdown. For example, if we were to use the previous example to try to calculate the fees in 2050, it would be an approximation, but without all the data between 2010 and at least like 2045 or 20, something closer to 2050, maybe our model, maybe our formula is not quite as accurate as it could be over the next 40 years. Okay, so model breakdown would occur here, and it's kind of a little common sense to see whether or not your formula is good for what you're using it for. Okay, let's go to sets. So before we describe the set of real number, we're going to talk a little bit more about the basic idea of sets. A set is a collection of objects whose contents can be clearly determined. Objects in a set are called elements. For example, the numbers of a set used for counting can be represented by 1, 2, 3, 4, 5, and then my ellipses right there means that it keeps going and going and going forever with this pattern. Sets, we're always going to use braces, right? And get used to trying to write them. Okay, takes a little bit of practice. Even mine aren't that perfect, but we're always going to use braces to enclose a set because parentheses and brackets we're going to use later to mean other things. So braces is what we're going to use when we are talking about a set. When we list the numbers out like this, that's called the roster method, right? We are just listing everything in the set. Even with the ellipses, we're just we're listing everything in the set. The other way to write a set is with something called set builder notation. In this notation, you just in roster notation, you actually write down everything in the set. In set builder notation, we just say what's in the set. So we're always going to put the variable. So it's going to be the set of x such that x is a counting number less than 6. So we put x, we put this line, and then we describe what x is doing in the next part of it. Okay? So when we take this set builder notation, when we take this description, all the counting numbers less than 6, that would be 1, 2, 3, 4, and 5. Okay? So you can go back and forth between roster notation and set builder notation. The set builder notation for this set right here would be all of the counting numbers, not just less than 6, all of them, because my ellipses means it goes on forever. So if A and B are sets, we can form a new set consisting of all elements that are in both A and B. So what is in both? And when we do this, that is called the intersection. So intersection of sets A and B written with this symbol, like that. Okay, so that symbol means intersection. The way you kind of remember that is, well, the next one that we're going to do is going to be a union, and that one looks like a U, so intersection is the one that doesn't look like a U. So this is the set of elements common to both A and B. A and B, it has to be in both. And the way I describe that with set builder notation is X such that X is an element of A and it is an element of B. And we can see that with the drawing is that the blue circle is all of set A, the pink circle is all of set B. This part in the middle is the intersection. It's where the two sets overlap. Okay, so find the intersection of the two sets. Okay, so that's what my little symbol right there means, intersection. And we just have to say what is common between the two sets. What is in set A and in set B? Well, I see a 7, but I don't see a 7 over here. Oh, look, I see an 8 in both. I see a 10 in both, and that's it. Okay, so my answer, set notation, would be 8 and 10. Okay, let's do another. Find the intersection, right? And there's my intersection symbol right in between them. So what is in both? 3, right? We got 3 in both. Is 4 in both? No. Is 5? No. 6? No. 7? Yes. So it's just 3 and 7. Okay? If a set has no elements, it's called the empty set or the null set, and it's represented by the symbol phi. Here's an example that shows an empty set can result when finding the intersection of two sets, right? What's the intersection between the two of these? 2, 4, 6, 3, 5, 7. There is nothing in between them. Now, if you want to write an empty set, this, oh, bad bracket, this is an empty set. This is not an empty set. It's got a 0 in it, okay? So if you write an empty set, it's got to have nothing in it. I would prefer just the null set symbol, the circle with a just slash through it. And I think we're used to that one. Okay. Another thing we can do for sets is form a union. So the union of two sets written A union B, right? So this symbol for putting the two sets together looks like a U. So that's how you remember it is the union, and intersection is the one that goes the other way. Is the set of elements that are members of set A or set B or both. So this definition can be expressed in set builder notation. A union B is A such that X is an element of A or X is an element of B. Picture. So we can see that A union B is all of the stuff in A, all of the stuff in B, all of the stuff in the middle, except we don't count the middle twice. So it's just this stuff, right? So when we list the two things, when we list the union, we just don't write numbers twice if they happen in both sets. Okay, so same two sets. So now, and it's nice that these two sets are in order, which you kind of should do every time you're writing sets, is try to keep them in numerical order. So we can say that we have 6, 7, 8, 9, 10, 11, and 12. I don't have to write the 8 twice and the 10 twice. I just take everything in set A in the first set and everything in set B, and I just put them in numerical order. Okay, so back to our checkpoint, same idea. So our union is 3, 4, 5, 6, 7, 8, and 9. Okay, so now that we know a little bit more about sets, let's talk about the sets of real numbers. So the sets that make up the real numbers are summarized in the table down at the bottom here. We refer to these sets as the subsets of the real numbers, meaning that all elements in each subset are also elements of the set of real numbers. So everything we're going to talk about is going to be a real number in this case. We'll get to numbers that are not real in a later section. Notice that the use of the approximation symbol in the example of irrational numbers, the symbol means is approximately equal to. So we can say that these two are not equal to each other. They're about, the square root of 2 is about 1.1414, that number. But it really is a decimal that goes on forever, right? And if you multiply it together twice, right, you don't quite get to. You get close. And in fact, this decimal goes on forever, which means it is part of the definition of irrational. So when we look at the subsets of numbers, we have our different subsets, and their sets we usually name with capital letters. So we have abbreviation names for each of the subsets of real numbers, and right, we usually abbreviate real numbers with an R, capital R, with two sticks on it. And these look a little fancier. Usually we just write them with capital letters, except for the real number one. We usually like to leave that with the two sticks on the side. So natural numbers. These are the numbers we use for counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, blah, 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 keeps going forever. Whole numbers, the set, and we abbreviate the set of natural numbers with an N. Whole numbers is all the natural numbers and also 0, and we abbreviate that with a W. Integers is all the whole numbers and their opposites, so and the negative numbers. Again, no fractions, no decimals in integers, and I is taken for irrational numbers, so we needed a different letter for integers, so we use Z to represent the set of integers. Now rational numbers is a over b such that a and b are integers and b is not equal to 0. So what that means is that rational numbers are now everything that can be written as a fraction. And the way you can tell is if it's actually a fraction, right? So like 2/5, if it's a decimal that stops, or a decimal that repeats. Pretty much the only thing that are not going to be rational numbers, that are going to be irrational numbers, are radicals that don't work perfectly. For instance, radical 4, square root of 4, is a natural number, in fact, right? And we always try to get as specific as possible. So it's a rational number because it's equal to 2. We can simplify it. But the square root of 2 is not a rational number. It is irrational. And of course, we can throw in things. Oh, we have pi over here. We can throw in symbols that represent fractions that never stop, like pi, like e. We'll talk about later. Okay? But as you can see from the chart, as you can see from the chart down here, all of these are real. All of these different types of. Oh, and I forgot to mention that rational numbers are abbreviated by Q, and irrational numbers abbreviated by I. So everything here is a real number. All of these different subsets are real numbers. Okay, natural is the most restricted. Then whole numbers is bigger than integers than rational. Irrational numbers do not fall. Irrational numbers and rational numbers are sort of like on opposite sides of each other. One can't be another. but an integer is a rational number. So there's no subsets inside of irrational numbers. However, there are many different subsets inside of rational. And I said this before, that not all square roots are irrational if you can simplify it. Okay, so the set of real numbers, if we're going to describe it in set builder notation, is all the numbers that are rational or irrational. So that would be a union. So x such that x is rational or irrational, and my symbol, my nice R symbol, is the union of the rational and the irrational numbers. And you can see that sort of this, put all the rational numbers together, put all the irrational numbers together, and we have all the different types of real numbers. So recognizing subsets of numbers. So we're going to now write all the different subsets. All these we have our set of numbers. We're going to put them into all the subsets. So for part A, the natural numbers. What's a natural number in here? Well, not 0. Okay. So it doesn't look like there is any natural numbers unless you are not careful, because that is a natural number. Okay. Not any better, because it's 9. Okay. B, the whole numbers. We now have 0 and the square root of 81. So we have 0 and square root of 81. I could write that as a 9 if you want, but better to just leave it in the form that the question put it to you. Integers. What are the integers? Well, other numbers, -7, that's an integer. And then everything else, right? 0 and the square root of 81. Those are still integers. So as we're getting bigger, right, we're just adding to the set and making it a little bit bigger. D, rational. Well, now we have more. So that's -7. -3/4, that's rational. 0 is rational. 0.6, repeating is rational because it repeats. So fractions that repeat are rational. Square root of 5 doesn't work. It's not rational. Pi is not rational. 7.3 is a decimal that stops. It is rational. And the square root of 81. Irrational is a little simpler. So we have the square root of 5 and pi. The only two that were not rational. And for real, right, this is the answer for real. They're all real. Let's try that one more time. So my natural numbers for this set is going to be the square root of 9. There are no positive numbers. There are no natural numbers here that are written anywhere else, but the square root of 9 is equal to 3. Whole numbers, which now includes 0. And my 9 is not that nice. Integers, we now have a -9, 0, and square root of 9. D, for rational, we now have -9, -1.3, 0. 0.3 repeating is rational. Again, pi over 2, it still has a pi in it. So even if you take a pi and you divide it by 2, it's still not, pi is a number that never stops. So that is not rational, and the square root of 9 is rational as well, which leaves my two irrational numbers, or E. My two irrational numbers are pi over 2 and the square root of 10, which is a square root that doesn't work. And again, they're all real. So next, we can talk a little bit about the real number line. So the real number line is a graph used to represent the set of real numbers. An arbitrary point called the origin is labeled 0. Select a point to the right and to the label it 1. The distance from 0 to 1 is a unit distance. As we go right, those are positive numbers. As we go left, those are negative numbers. And real numbers can be graphed on a number line by placing a dot in the correct location for each number. Any real numbers, rational numbers all up on the top, okay, irrational numbers in the bottom, approximations but you still can put it on the number line. The only thing we can't put on a number line is imaginary numbers, because this is the real number line. It only has numbers that are real. If we did have an imaginary number, it would sort of be off the real number line, either above or below, depending if it was positive or negative. Okay, we'll talk about that later. So every real number corresponds to a point on the number line, and every point on the number line corresponds to a real number. This is a 5, right? This is 5 point whatever, 2. Okay, so no matter where you go on the real number line, it has a number that corresponds to it. And that means there's a 1-to-1 correspondence between all of the real numbers and all the points on the number line. Okay? To order real numbers on the number line, they increase from left to right. Pretty standard stuff here. So if we look at -4 and -1, we can see that -4 is to the left of -1. On the number line, that means -4 is less than -1. And we can write that with a symbol that means less than. We also can observe that -1 is to the right of -4. So that means -1 is greater than -4, and we can write that with that symbol, the greater than symbol. And those two symbols are called inequality symbols. And these symbols always point to the lesser of the two real numbers. Or, you can always think of like an alligator or Pac-Man or something like that that always wants to eat the bigger number. Okay, so you should be fairly familiar with the inequality symbols. So the symbols less than and greater than may be combined with an equal sign, as shown in this table. So symbol is less than or equal to, and greater than or equal to. Okay. Changing to absolute value. So absolute value, we just talked about distance, right? In real number lines, absolute value of a number A is denoted with the absolute value bars, and it is distance from 0 to A on the number line. And this distance is always taken to be non-negative. For example, on a real number line shows that the absolute value of -3 is equal to 3, because to go from 0 to -3 takes 3 spaces. If we have my number line, 0, -3, right, 1, 2, 3. Yeah, we're going left, but we're still moving a distance. And same thing with 5, 1, 2, 3, 4, 5. So 5 would be positive as well. Okay? And that's what the next paragraph says. Okay? So we can define absolute value without referring to a number line. And the definition of an absolute value is best defined with a piecewise function. So the absolute value of x, the absolute value of whatever is inside these bars, is always the same thing if x is greater than or equal to 0, or opposite if it is less than 0. Okay, so while you might say, well, negatives never come out of an absolute value, yeah, you're right, because if we have a negative inside the absolute value, then I would do, just like this is talking about, we would do -3. The absolute value of -pi is -pi, +pi. No one ever does this, right? We don't really ever have to write this out in this manner. We can just say, okay, there's a negative inside of the absolute value. We can make it positive. Okay, so usually we omit that step. Sometimes, however, we have to really think about what the absolute value actually means. So in this case, the absolute value of the square root of 3 minus 1, I have to ask myself, what is the square root of 3 equal to? Because this is an irrational number and a rational number. I can do a calculation with them, but I should leave it in this form. And so if I realize that the square root of 3 is actually equal to like 1.7, if I'm going to subtract 1 from that, I'm going to get a positive number, which means that this doesn't change. So these are, it's just equal to, now I could just write 0.7, but I want to leave it in this form because 0.7 is a approximation. Radical 3 minus 1 is an exact number. So I want to leave it in the form of an exact number, but I don't have to change anything because I know it's positive. That's different with part B because I should know that pi is 3.14. So 2 minus pi is going to be a negative number, which means from our definition before that I'm going to take whatever is inside and take the opposite of that. Okay, so that turns into negative 2 plus pi. And I can always rewrite this. Usually we want to have the lead term be positive if we can, and I can use, I can just put them in a different order. Okay, I can use commutative property. So basically what this says is that if I have a rational, irrational number, or if I have a combination of the two, if the sum or difference would be, or difference usually, if the difference would be positive, I leave it the same. If the difference would be negative, it basically switches the sign of both, and I sort of flip it around. For part C, we have to use a little algebra. So if x is less than 0, the top term is going to turn into negative x, right, by definition. And that's over x, so this would be negative 1. Let's try those again with my checkpoint. 1 minus radical 2. Radical 2 is 1.4, so this is going to turn into radical 2 minus 1. Pi minus 3, pi is 3.14, so this is going to be positive, so it just stays the same. And if x is greater than 0, the absolute value of a variable is just that variable, so this is equal to 1 by definition. So below are several basic properties of absolute value, and each of these properties can be derived from the definition of absolute value, and they're mostly pretty self-explanatory, except for the last one. Probably might not have seen that one before, but the absolute value of a is always greater than or equal to 0. Okay, makes sense. The absolute value of negative a is equal to the absolute value of positive a. If they're the same distance in different directions, the distance is still the same. A is less than or equal to the absolute value of A. That is always true. A times B, absolute value of that is equal to the absolute value of A times the absolute value of B. Even if they're positive, even if they're negative, the absolute value signs are going to make everything positive in the end. Same with the division. Of course, B cannot be equal to 0. And my triangle inequality is the absolute value of A plus B is always less than or equal to the absolute value of A plus the absolute value of B. Distance. Let's talk about some distance. Absolute value is used to find distance between 2 points on a number line. If A and B are real numbers, the distance between A and B is the absolute value of their difference. So either way you do it, if you take 10 minus 4, you get the distance between those two is the absolute value of 6. Or if you do 4 minus 10, which is negative 6, the absolute value of that is 6 as well. So distance, you just take the 2 points on a real number line, subtract them, and take the absolute value. Now, a good habit to get into when we're finding distance and when we're going to start to use, slopes, and we're going to start to use graphs and things, we always want to usually go left to right. So it's always going to try to do x2 minus x1 if we're going to work with numbers on a real number line. So we want to take the one further to the right minus the one further to the left, right? As we go, one would come first, then 2. Okay, so we would usually go 3 minus negative 5, all right, to get, and then of course we can absolute value, which would give me 8. We don't have to do another one of these. Distance should be really no problem for anybody to calculate. So properties of real numbers and algebraic expressions. So when you use calculator to add your real numbers together, you can enter them in any order, right? Because we have something called the commutative property of addition, right? You probably use this property as well of other properties without even thinking about them, right? But you should know that they are out there and they exist. Properties of real numbers are especially useful when working with algebraic expressions. So here are all my properties. Commutative property of addition just means that changing order does not affect the sum. We can add them up in any order. Multiplication means that we can multiply them in any order. Associative property of addition means that changing the grouping when adding does not affect the sum, right? A plus B and then plus C is the same thing of adding A plus the sum of B plus C. Same thing with multiplication, right? All these properties, commutative, associative, right? We say the property of addition if it has addition in it, multiplication if it has multiplication in it. Distributive property is going to have both. The distributive property of multiplication over addition means that A gets multiplied, right? You can see it with the blue lines. A gets multiplied to both B and C to make A times B plus A times C. And all of these properties work with variables. They work no matter if you have rational numbers, irrational numbers, whatever you have, it still works. Identities and inverses. Let's talk about those for a second. Identities are things that when you do the operation, nothing changes. So the identity property for addition or additive identity is what you add to something to get the same thing, to make nothing change, and that's 0. The multiplicative identity is the thing you multiply to something and make nothing change, and that's 1. So the two different identities depend on what operation you're doing. Is it addition? Is it multiplication? So addition, the identity is 0, and multiplication, the identity is 1. Inverses are the thing you do to a number to get the identity. So if you start with a number A, how do you get the additive identity which is 0? So you would add the opposite. Okay? So the inverse of A is always negative A, or the inverse of negative A is positive A, because when you put them together, you get 0. And the multiplicative inverse is the thing you do to a letter to get the identity, which is 1, and you multiply by its reciprocal. So A times 1 over A would give you 1, and 1 over A, if you started with a fraction, times A would give you 1 as well. Now, you might notice here that all of these properties talk about multiplication and addition. Well, you're probably thinking, what about subtraction and division? So all of those properties are extended to subtraction and division as long as we think about subtraction and division in terms of addition and multiplication. So our number system, the way it works, really only has those two basic operations, addition and multiplication. Subtraction is when we add an inverse of B. Okay, so you can take two numbers, A minus B, and you can see that it is the same thing as A plus a negative B. Okay, which means all of those properties before hold for subtraction, because subtraction is just the same thing as addition. Now, I'm sure you've heard this in going way back, that the commutative property is not true for subtraction. Well, it's not true if you write it the wrong way. That is absolutely not true, okay? A minus B is not equal to B minus A, because in the first part of the expression, the B is negative, and in the second part of the expression, the B is positive. Commutative property does work if you keep the signs the same, or if you think of subtraction as adding a negative number. Now, right, so we can always say that this is true, okay? And the same with division. Division is just multiplying by a fraction, okay? The multiplying by the multiplicative inverse or the reciprocal of a number b. So a divided by b is the same thing as a times 1 over b. And if you think about the way numbers work in this way, then all of the properties that we talked about on the last page all hold for subtraction and division. So because subtraction is defined in terms of adding an inverse, the distributive property can also be applied to subtraction as well, right? So just same thing. And we can distribute from the front or from the back, it doesn't matter. Normally I would say, it's good to go left to right, so it would be b times a negative c times a, but it really doesn't matter if you want to distribute either way, okay? So to simplify algebraic expressions, we can break it up into terms, and the terms of an algebraic expression are those parts that are separated by addition. Remember, subtraction is just adding a negative number, so all of this expression is separated by addition, okay? It's 7x plus a negative 9y plus z plus a negative 3. Now, we don't really have to write it all out like that, as long as you understand that that's how we are defining the terms of an expression, is just with addition. And then you can think of it as, well, okay, addition or subtraction. The numerical part, so this has 4 terms. The numerical part of each term is called its coefficient. In the term 7x, the 7 is the coefficient. If the term containing one or more variables is written without a coefficient, the coefficient is 1, like z. Z has a coefficient of 1. And if the term is a constant, its coefficient is that constant. So the coefficient of the constant term, negative 3, is just negative 3. The parts of each term that are multiplied together are called the factors of the term. So for 7x, the factors are 7 or x. Like terms, should have heard that before, are the terms that have exactly the same variable factors. For example, 3x and 7x are like terms, and you can combine them using the distributive property. Okay, so what we're really doing when we add like terms together is we are factoring out the x, we're taking it out using the distributive property, and we're adding the 3 and the 7 together, and then leaving off with 10x. Now, again, you don't have to go through those steps every time, but just understand that that's sort of the method that is being applied, the properties that are being applied in order for us to combine those like terms. Okay? And an algebraic expression is simplified when all the parentheses have been removed and all the like terms have been combined. So, to simplify this algebraic expression, what my goal is to get rid of all the parentheses to combine all the like terms. So I'm going to start with the distributive property here, and I'm going to go 12x squared. I'm going to multiply this to both of them, plus 24x, and now I'm going to distribute the 10 plus 40x squared plus 30x, and now let's do this the exact method, right? Again, we can just say, oh, just combine the like terms, but what I'm really doing, I'm just going to do this once, is I'm rearranging the expression using the commutative property. Okay, then I am taking out the x squared and the x using the distributive property, and then I'm combining just the numbers and putting them back together. So this would be 52x squared plus 54x. And again, you don't have to do all of that each time, but just realize that that is the method that we are using to combine them. Let's try another one. So we have 28x squared plus 21x, distribute the 2, 10x squared plus 2x, combine the like terms, and it's better, we'll talk about this in another section, but it's better to list the terms in the biggest degree, biggest exponents first. So that would be 38x squared as I combine those two, and 23x. And again, those two cannot go together because these two are not like terms. Okay, properties of negatives. Distributive property can be extended to cover more than two terms within parentheses. So you can see you can distribute the -3 all across the expression, and what it has the effect of changing the sign of all of the different terms. Okay, so again, so this sign is subtraction, and then we're multiplying it by -3, so that means it turns to addition, right? Minus and minus. Here are my properties of negatives, right? -1 times a number is equal to the negative in front of that number. Negative times a negative gives me a positive. Negative number times a positive number means that now that product is negative. Positive times a negative means the product is negative. And then I distribute those two, distribute these two, and I can write that expression. I can use the commutative property to flip that around and write the b first so that the leading term is positive. Depends on the situation whether or not you want to do that. So it's not uncommon to see algebraic expressions with parentheses preceded by a negative sign or subtraction. So that would be those two, 5 and 6. And in this case, it's just simplified just by distributing the negative, just multiplying a -1 across the whole expression. Right? Do you see a fast way to obtain the simplified expression? If a negative sign or subtraction symbol appears outside parentheses, drop the parentheses and change the sign of every term within the parentheses. And that's usually the most efficient way to simplify, right? So we have our expression here. First one becomes negative, positive, positive. Change the sign of each term. So let's simplify this expression using some order of operations and combining like terms and all of that fun stuff. So we're going to have to go inside the parentheses first. There's nothing I can do there. This negative is going to get distributed to these two. So that's 8x plus 2 times, and in an algebraic expression, sometimes you might see parentheses and then brackets. It's just nested parentheses. You can change them back and forth however you want. So -5 minus x plus 3 is the easiest way to simplify that. 5, so that becomes 8 minus x. Distribute the 2, whoops, 16 minus 2x. And now the like terms can be put together, and we get 6 plus 6x plus 16. Okay. And finally, our last problem here, same idea. 6 plus 4 times 7 minus x plus 2. And combine the like terms, so 6 plus 4. So that's 9 minus x. So that's 6 plus distribute the 4 across. And 6 and 36 gives me this, right? So we're going to lead with a negative, but it's okay because it has a higher degree. So 4x minus plus 42. Okay, you can also put 42 minus 4x. Doesn't matter. Okay. And that is the end. This was a rather long section, I know, but that was section P.1, algebraic expressions, mathematical models, and real numbers.